Good. We are now doing GM2a. Ghosh Mallik, third edition, chapter 2, first video, and it's a reading companion for that. Right? We are doing kinematic analysis. In particular, we are doing displacement analysis. Within that, we are doing geometric methods. Now, if you are a modern kinematics designer, then you will use a computer. However, in terms of transferable skills and older methods and insights and so on, these are great. So I like these and tend to appreciate them and emphasize them. Okay, all right, very good. We will begin with a sort of basic problem, which is range of motions. Okay, let's start with a 4-bar mechanism with the following dimensions for definiteness. My pictures are not going to be on to scale because I'm drawing them by hand, but I hope you will not have trouble in understanding the calculation that I'm describing. So as you can see, it's not perfectly in proportion, but let these be the dimensions. This is the input link, this is the output link, this is the coupler. Is this a Grashof linkage? Smallest plus largest is 3 plus 7. This is less than 5 plus 6, so this is a Grashof linkage. What does this mean? This means that this one can make a complete revolution. This will rock. So it will have a range of motions, and I am interested in finding that range of motions of this link whose length is 5. Okay. For example, could it come all the way down here? Could this link come here? Well, then 6 and 5 would make 11. While 3 plus 7 is only 10. So that's not possible. That means it will stop somewhere here. Where will it stop? It will stop where this link of length 3 and this link of length 7 become collinear, because that is as far as it can go. With that supposition, let me take green here. 3 plus 7 is 10. So this being 6, that's about 10. Let me draw an arc of radius 10, and over here this point of course still moves in an arc of radius 5, so this is the extreme position. Let me mark that in blue now with a fatter brush size, and so that is 3, 7, total is 10, this is 5. This link cannot come over here, and this is the clockwise max position. Okay. Similarly, you can see easily that there must be a left side position. The left side position also corresponds to these links being collinear, but in a different way. To understand why they are collinear, let me remind you that this point is fixed here. This point is fixed. This point therefore has a velocity that is perpendicular to this rod. Relative to this point has a velocity that is perpendicular to the rod. These two being in the same direction, the velocity of this point must be along this rod. Yet it is also pivoting about this point, and so the velocity must be along this direction also. The only way it can be in this direction as well as this direction is if its velocity is 0. This tells you that even when this has a non-zero velocity, this has a zero velocity. That is precisely because it is at an extreme position. Okay, that part is clear. Let's make this thin again. Let's draw this again over here. Okay, for the leftmost extreme position, this length 3 and this length 7 must be collinear again, but they are collinear in the other place. By which I mean the 3 will be over here and the 7 will go back. So over here the effective length will be 4. One way to do that is to take this distance as 4 and draw a circle. From here you extend this arc and it cuts here. This is 4, this is another 3. This link has now come here, it has gone back up 7 units, it has reached here. This is the counterclockwise max position of this link, which again I will take blue, take a fat brush and mark this here, which corresponds to that position. Okay, very good. I'm going to now take it to be green and a bit thinner and just mark this line here somewhere for your reference, for a simpler observation. But now here I have this one, I'll mark that here in a parallel position. So here this I will shade as green. This is the angular range of motions. I'll also point out something, that from the extreme position at which location the crank was here to the left extreme position where the crank has come from here up to here, this angle can be called theta f. It's the forward stroke, and from here to here we can call it theta r, the return stroke. Theta f is bigger than theta r. Theta f over theta r is called the quick return ratio, happens to be greater than 1. Another idea that we will take away with us is that when we are looking for an extreme position of this link, for example, the other two links are collinear. When we are looking for the other extreme position of the same link, once again the other two links are collinear. This idea will help us in the next problem we tackle, which is a non-Grashof linkage. Once again, let me take a smaller brush size, and this time I will use the dimensions 3, 6, 8 and 4. Once again, not to scale. This picture is not to scale, it's hand drawn. I am using it to illustrate principles. This one is fixed here, this one is fixed here. These are not numbers of links, they are dimensions. The smallest is 3, the longest is 8. 3 plus 8 is greater than 4 plus 6. This is the non-Grashof linkage. This means that both of these links, 3 as well as 4, they are both rockers. Alright, let's find their maximum positions. Quick question. Can this come all the way here? If it comes here, 6 plus 4 is 10, 3 plus 8 is 11. Such a configuration is definitely possible. So this will therefore cross this horizontal position. This link will cross the horizontal position. But on the other hand, can it come here? Well, it can't come here, because if the 4 comes down all the way here, only 2 is left. 2, 3 and 8 cannot make a triangle. That means this has a limit. It can't come to this side. It can go to this side, and somewhere over here it has a maximum. What is that maximum? Well, 6 plus 4 is 10, 3 plus 8 is 11. We know they have to be collinear, but they can't be in the stretched out position, so they have to be in the overlapping position. 8 minus 3 is 5, and so over here, let's say that is 5. Suppose I draw a circle of radius 5, and this one is 4, so I draw a circle of radius 4. They intersect somewhere here. Now I will use red. So from here to here is 5, from here to here is 4, and this is the counterclockwise max position. I will use a fatter brush to mark this one down. This is 5 here plus 3 here. Remember, this link went all the way there and then came back here. Alright. As there is a symmetrical arrangement on this side, which I will leave dashed, this link of length 4 can cover this entire area. Using calculators or graphical methods, you can find that angle, but I am now just trying to tell you what that angle is conceptually. Very good. Now let's look at link 3 and try to find its extreme positions. Can it come to this side? Well, 6 and 3 is 9, 8 and 4 is 12, so it can definitely come to this side. Can it come to this side? Well, if it comes to this side, what happens is, when I remove this 3 from this 6, only 3 is left. This 3 and this 4 makes 7, and that is 8. 3, 4 and 7 cannot make a triangle. Therefore, it can't come to this side. Therefore, this link of length 3 has a range like this. I have found the range of motions of link 4. Now I am interested in the range of motions of link 3, for which I will use a blue color. Once again, for its extreme positions, I want 8 and 4 to be collinear. If 8 and 4 are non-overlapping, that is 12. That is too far. 6 and 3 is 9. Therefore, they are overlapping. 8 minus 4 is 4, which by coincidence is the same 4 as this. So that is this 4, the same dimension. On the other hand, this 3, I can draw another arc and it will come to the midpoint, and so it intersects somewhere here. For this reason, this is the 3, that is the extreme position. Here is 4, another 4, turn around, and 4. That is the configuration. This is the extreme position. There is a symmetrical configuration over here. This one is the angular range of this link. Okay, so that is this problem. Let's do another one. Next problem, also non-Grashof. Let's take a thinner brush, different color. Let's try this one. 3, 5, 7, 11. Shortest is 3, longest is 11. 3 plus 11 is greater than 5 plus 7, non-Grashof. Okay, these will also rock, both of them. Can this 7 come all the way here? Well, that length will be 18. This is only 3 plus 5. That's not possible. Can this 7 come all the way here? Certainly, because when it does, 4 will be left here. This 4, this 3 and this 5 can make a triangle. Okay, so the 7 will come here. So its range, now you see, is here is the range for this link of length 7, and it can't go to that position. Compare with the situation here where it was going in that position to the right side. Here it will go to the left side. It will move inwards. Over here it was moving outwards. But let us find the maximum position. That is easy. Now, because this arc of length 7, radius 7, 3 and 5 collinear make it 8. So then that is about 8 here. That's the length. And so here 3 plus 5, sorry, this 7, this 8, all right. That gives you, this is 3 and 5. 3 and 5 make 8. Okay, this is the maximum position of this link. This link also has a symmetrical position on this side. It passes through this location. This is the angular range of its motion. How about this one, the 3 one? Okay, so let's look again at the 3 one. Let's make a thinner link. Let's draw this picture again, maybe with blue. So here we are, 3, 5, 7, 11, all right, 11 and 3 make 14, 7 and 5 make 12. That means this cannot come all the way here. Suppose it comes here. 3, if I remove from 11, I'll have 8. 8, 5 and 7 can make a triangle. Therefore, this is inwards also. Okay. Compare with the previous one. In the previous one, here it was outwards, here it was outwards, here it was outwards. In this one, here it is inwards, and here it is also inwards. Very good. Now let us look for the maximum position. To find the maximum position, let's use yellow here. 7 and 5 collinear make 12. This is 11 already, just slightly bigger than that. That is 12. You draw this arc over here, that's 12, and then here with the 3 you draw another arc. It cuts over here, and so 3 and 12. Okay, and so now I will have a fatter brush size, red color here and symmetrical here. This is the range of motion for this link. Okay, let's do another one. Okay, let's do this one. Smaller brush size, light blue color. Let's do 3, 4, 10. 10, and 12. Okay, is it Grashof? 3 plus 12 is 15, 10 plus 4 is 14, 3 plus 12 is bigger than 10 plus 4, non-Grashof. Both are rockers. Fine. How about this one? Can it come all the way here? Well, no, because 12 plus 4 will be 16. This is 3 plus 10, 13. So this will come this way, right? So this will have a range of motions like this. Let me mark that in yellow so that it is clearer. How about this one, this position? Can it come here? If this came all the way here, then there would be only one left. 1, 10 and 12 cannot make a triangle, so it can't come here. Can it come to this side? Well, 4 and 3 would make 7. 7, 10 and 12 can very much make a triangle. So this link here has motion like this also. So now this one is outward and this one is inward. This is different from the other two examples. Alright, let's find the range. The range, this is easy. You see, the maximum for this one, this 3 and this 10 have to be collinear. So what I do is I take some, and this has to be 12 this distance, so I take this arc, and from here I draw another arc of radius 13. Wherever it intersects, that gives me the extreme position of this link. Okay, this is the angular range of its motions. Very good. Now how about the angle? Let me mark it nicely with fat color here. So this is the angular range. There's going to be similarly another one here. This is the angular range of this link whose length is 12. One got hidden, right? Okay. How about this one? So for this one, let's try green. For this one, once again, for the extreme motion of 3, 10 and 12 must be collinear. But for 10 and 12 to be collinear, what is needed is the 10 overlaps with the 12 and there is just 2 left. So let's do here 3, 4, the 10 is like that, the 12 is like that, minus 10 is 2, which is half of here. So let us do this distance, because that is what we will have where this position will be. When 10 overlaps with 12, that point will move from here to here, wherever, somewhere. It has to be on that circle. This point must also be on this circle. Therefore, it must be here, which means that is what the location will be. This one now I can draw with a bigger brush, blue color. Okay, this much is 2, this much is 10, this is the 3 part. You may find it a bit odd to see it like this, but let me remind you, this point is fixed, therefore the velocity of that is perpendicular to the line. The velocity of this point relative to that point is perpendicular to the line. Therefore the velocity of the whole thing is perpendicular to the line. Yet it must also be perpendicular to this line. This means that the velocity is 0. That shows it is an extreme position of 3. Let me get rid of some of these extra velocity markings. Okay, so that's the extreme position. And then how does it can't come here, as we have discussed, because that will leave here 1, 12 and 10. So it does cover all this distance and it comes to this side. Okay, so that is the angular range of this link. All right, look at this carefully because it is a bit surprising. So look at it a bit carefully. The range of this link is the full value from here to here. The range of this one is the full range from here to here. This link actually goes like that, right? So if I superpose this red one here, you will see that this link actually has a large range, out of which this one has a different range. It is just this part. Okay, this one completes the full circle. With this introduction, I can now do a slider crank mechanism, which is discussed in the textbook and which I found a little difficult to understand until I went through these simpler examples. Okay, so now we will do this problem. We will do this problem here, different color. We will do this problem here, 3. Let's do 4. Let's do 2. And this here is a slider. All right, this is the input link. We want to find the range of motions. Well, let us think of this slider through the equivalent 4-bar linkage. So what happens is this slider always moves perpendicular to this line. Okay, for this reason, what we should do is somewhere effectively at infinity, some distance L infinity away, we should think of a hinge B that is attached to this body. This body and this body, hinge B, are the same body. Okay, and from that hinge B, we should have this one, we should have this one. So let me mark it in red for you. This link, this link, this link and this link are taken as an approximating 4-bar linkage for this slider and this 3R1P linkage. Okay, the approximation becomes exact when L infinity goes to infinity. Let me point out something to you. Because of this distance, there is this length, and you may wonder what that is. So let me point out. If I have a fixed length P, doesn't matter, and if I have another length L0, and if I have this third length L, then L is equal to the square root of L0 square plus P square, which is L0 times 1 plus P square by L0 square to the power half, which is L0 1 plus P square by 2 L0 square plus even smaller terms. And you can see that even after you multiply by this L0, this will be P square by 2 L0. If you hold P fixed and take L0 to infinity, this term will in fact go to 0. and L will become equal to L0. That is why in this direction, when B is taken to infinity and we think of L infinity as arbitrarily large, this basically just becomes parallel, which is what is shown in the book. Very good. Is it Grashof? Okay, so the smallest link is 2. No, not 2. This is L infinity plus 2. The smallest link is 3. 3 plus L infinity plus 2. That is the longest link. Has to be compared with L infinity plus 4. The L infinity cancels. 5 is bigger than 4. Therefore, this is also non-Grashof. Very good. For this non-Grashof linkage, I now want to find out what is the range of motions. So I will remind you, this goes off to infinity, this goes off to infinity, it's going off to infinity somewhere. All right. Now, when I want let's do this. Can this one come all the way here? Yes, it can, because this is 7 and these are two very long links, and one is slightly bigger than the other, but not that much bigger, because this is L infinity, this is L infinity plus 2. So this position is definitely possible. How about this position? This position is not possible because this is 3, this is 4, so that will leave 1. You can't have L infinity, 1 and L infinity plus 2 in a triangle. Okay, so we know that it can't come all the way here. It can go like this. It has an extreme position. At that extreme position, which may be somewhere here perhaps, at that extreme position, what is the angular position of this rod? What is this angular position? Well, at the extreme position, L infinity and L infinity plus 2 must coincide. When they do, it is effectively a radius 2 from here. L infinity plus 2, back L infinity, down to radius 2. Okay, so it is somewhere there. At the same time, this hinge has to be on radius 3, so it has to be here as well. So at this intersection of the circle of radius 3 centered here and the circle of radius 2 centered here, this is the extreme position of this link. Let me mark it with red. So this is the, make it fatter. This is the extreme position, and here to infinity is this linkage, which means that actually the slider is in this direction, but we will think about that later. Okay, so that is one issue that we have sorted out, is the extreme position of this. It will go like this and come around all the way to this side. Now let us think of the extreme position of this link. Back to a thin pen and a blue color. When we look at the extreme position of this one, then these have to be collinear. Okay, now when I make them collinear, where do I, what is the, when I'm looking at the extreme position of this one, these two have to be collinear. Okay, very good. This is L infinity plus 2, this is L infinity plus 3 when it is collinear, and this is 4. That triangle is possible. That means that basically these will become parallel. Okay, but when they are parallel, what is interesting is that this remains on this link of length 3. Then from here, there, that is L infinity. This is also L infinity plus 2. So if I draw a circle of radius 2, there is a common tangent. That common tangent tells me this limiting position. Okay. After I find that limiting position, I can make this pen bigger. Once again, let me remind you, circle of radius 3, because this pin has to be there. Collinear, therefore it is straight and parallel to this one. This is L infinity plus 3, that is L infinity plus 2. So subtract, difference is 1, right? So then over here you take radius 2, you draw common tangent. This defines this position here, blue color. This fatter because it's a bit overwritten. This blue, this blue. This is the angular position. Okay, so we were actually trying to find the angular position of this one, so that's where it is. That is the angular position of this one. This is the angular range of the other one. And so now we come back here to this problem. 3, 4, 2, and a slider, and what we find is that the angular range of this one is given by this circle. Over here we have to draw this angular circle of radius 2. The angular range of this one in red and fatter is from here to here with its common tangent. The angular range of this one, I will do with mauve, is this. This example is in the book. After this discussion here in the video, you may be able to follow that example better. There is a final example that I would like to do, which is also there in the book, and that is a Whitworth quick return mechanism, which looks like this. So this mechanism has one hinge here, another hinge here. From here there is a long link, which is as long as it needs to be, and then from here there is another rather long link. There is a slider here. So this slider is hinged to this rod. This is O2, this is O4, O2 to slider A. This is a rod here with a hinge here. There's a horizontal line here. Another link and a slider. Okay, this point we can call it C, this slider we can call D. This is the input link which moves at a constant angular velocity. As we move it, D has a leftmost position which we will call XL. It has a rightmost position which we will call XR, and there is a quick return ratio. This is the Whitworth quick return mechanism. It's there in the book. How do we find it? Well, what I will do is I will first point out that this point here has to move on this circle. Whether it can access all points on the circle, we will determine soon enough. But it has to move on this circle. And this point here has to move on this circle. And if this length is L, then wherever C happens to be, C to D, the distance is L, and D has to move on this line. Okay? Alright. Let's try something with maybe this purple color. Not purple, it should be a light color, maybe blue, yellow. Let's try something with yellow. Just make it a bit fatter and we'll eliminate it soon. So let us say that the slider has moved here. When the slider has moved here, this link then has to be like this. Point C has to be there, and D is there. No difficulty. Okay, let's say this has moved here. Okay, so this link is then there, the point C is here, and the slider is then somewhere. No difficulty. In this way, this point C will eventually reach this position here. That is the furthest to the left it can go. Corresponding to that, so if this radius is R, this radius is R, and that is L, then you see XL is equal to L minus R. That is determined. When that happens, this slider has to be here. Now the slider keeps going. The slider rises here now. Then what happens is this point C has come here. It has moved a bit to the right, and this is again come to the right somewhere. Then the slider goes somewhere, C comes here, slider goes somewhere else, C comes here. And when the slider reaches this other point, that is where this C is here, and then L further out, that is XR. So XR is equal to L plus R. So that range of motions is also determined. What is more interesting also is that the forward stroke is, now let me use a fatter pen because I'm nearly at the end. So from here, this horizontal line is of great importance. This hinge point is of great importance. This corresponds to the leftmost position. All this way to here, this corresponds to the rightmost position. So this is theta F. And then from here to here, this part is the theta R, where it goes from the rightmost to the leftmost. Geometrically, we can now find this theta F over theta R is the quick return ratio. Alright, that's enough for this lecture. Thank you.